So Bulletproofs is joint work with Jonathan Bootle from University College, my advisor Dan Benet, and Andrew, Peter, and Greg, who are Bitcoin core developers. So consider a Bitcoin transaction or most cryptocurrency transactions. They have this sort of format where you have some inputs to the transactions and some outputs to the transaction. And you can see that one important quality of an input of a Bitcoin transaction is that the inputs are greater than the outputs. And that is important because no new money should be created in a transaction. There should be no inflation. So, and the inputs here are on the left and the outputs are on the right. And the difference is actually the fees, the difference between the inputs and the outputs are the fees that are paid to the miners to validate the transaction. So how does a miner validate a transaction? Well, a miner or any sort of full node can validate a Bitcoin transaction by checking that the signatures are correct, so a person was authorized to spend the money. Secondly, that the inputs are unspent, so you cannot spend the same money twice. And then thirdly, that the sum of the inputs is equal to the sum of the outputs plus the fees. The problem with a Bitcoin transaction is that the transaction amounts are available in the clear. So what does that mean? It means that, well, there's also other information like the payer and the payee that are available. But what does this mean? It means that if I receive my salary in Bitcoin, then everybody can see what my salary is. And additionally, if I'm, say, a business and I'm buying supplies for my company, everybody will be able to see how much I'm paying for these supplies. So if I buy tires as Ford, then everybody will be able to tell how much am I paying for these tires. And these are important business secrets that you would not want to have on a public ledger like a blockchain. So this is at least the preventing that the transaction amounts are public. The idea is called a confidential transaction. So how can we hide these transaction amounts? We use something called a cryptographic commitment, or specifically a Patterson commitment. And it has the two properties that it is hiding, it doesn't reveal what the amounts are, and it is also binding. So once I commit it to a value, I cannot open it to another value later. The problem is if this transaction now has committed values, I just said the amounts are hidden, well, how do you check this condition that the inputs are equal to the outputs plus the fees? And additionally, there's a second condition that I didn't mention before, is you have to check that all of the outputs are positive, right? That not one of the outputs is negative and the other one is much larger. And this actually turns out to be the more difficult condition to check. So when cryptography comes to the rescue, we can do this using a non-interactive zero-knowledge proof of knowledge. So Peggy, a prover, can use a common reference string that is available to both the prover and the verifier and create a proof that the committed value that she committed to is actually positive. This is, say, the proof for the output. And Victor or anybody can check the proof for this commitment and be convinced that the value x that was committed to is positive. But it's zero knowledge in that Victor doesn't learn any other information than the fact that the value x is positive. So Victor, most importantly, doesn't learn what the precise amount is. So this concrete scenario is called a range proof, because I'm proving that a number is in a small range, which implies that there's no overflows possible. So currently, the range proofs that are used are based on something called a sigma protocol, and they're linear sized. And what that means is they're linear in the bit length of the range. So if I want to prove that my number is between 0 and 2 to the 64 minus 1, then I have to use something that is about 64 elements, or something that is linear in 64 elements. And this turns out to be roughly 4 kilobytes, and even with some recent optimization. The nice thing about sigma protocols is they have no trusted setup. There's some proof systems that are much more efficient, like snarks, but they unfortunately rely on something called a trusted setup, where a party creates a proving key and a verification key. And the problem is, if this was done maliciously, then someone can create fake proofs, so proofs about statements that aren't actually true. So these sigma protocols that do not have a trusted setup, but are quite large, and actually prohibitively large, probably, to implement such a system or implement confidential transactions practice. So this is where we introduce bulletproofs. So bulletproofs are built on previous work from UCL that was published at EUROCRYPT 16, and they use a so-called inner product argument, and we improve the inner product argument from the Bootle et al. Paper. So what is this inner product argument? Well, it's a proof that, say I have a hash to two vectors, A and B, and a scalar C. And it is a proof that the inner product between A and B is this value C. But the important property of it is that it is logarithmic in the size of the vector. So to convince you that this statement is true, I only need to send you 2 log n cryptographic elements. So these elements are 32 bytes if you use 128-bit security. And this improves from the previous version, which was 6 log n. And we also enable proofs on committed value. So right, if you remember what I showed you previously in the confidential transaction, I have to prove that the value x, which I was previously committed to, is in some range. And I can now directly do a proof on that statement rather than implementing, say, the commitment algorithm or the opening algorithm in my proof system. It also only relies on the discrete logarithm assumption and doesn't have a trusted setup. And overall, this leads to a range proof, which is 2 log n plus 9 elements for a range proof, where n is the number of bits in the range again. But bulletproofs doesn't only work for range proofs. You can do sort of arbitrary proofs, proofs for arbitrary functions, which are formulated as arithmetic circuits, so circuits with multiplication and addition gates. And there, the proof size also improves from the previous scheme, the Bootle scheme, and is 2 log, also scales with 2 log n, where n is the number of multiplication gates. So let's compare. What does this look like? Well, for a single 64-bit range proof, now suddenly the proofs aren't 4 kilobytes anymore. They're 670 bytes. But the nice thing is that a transaction, as I showed you before, usually has multiple outputs, right? I send some money to a friend of mine, and then I send some money. The change goes back to me. So if I have 2 outputs, I can actually create a so-called aggregated range proof. So I create a proof for these 2 commitments that both of them are in the right range. And then the proof size, because of the logarithmic scaling, only goes up by 64 bytes. Versus the old range proof, which scaled linearly. And we can extend this game for 10 range proofs. Now suddenly it's still less than a kilobyte for bulletproofs, but much larger for these old range proofs. And I also show snarks here, which have actually constant size proofs, so they're even better. But again, they have this downside of a trusted setup. So how do we get these transactions with large, sort of, where we have a large number of outputs, right? Like sometimes maybe for Christmas I'm sending all my relatives some Bitcoin and I have a large number of outputs in the transactions, but usually transactions have more like 2 or 3 outputs. Well, what is common though is that there are multiple people that want to create, that all want to create an individual Bitcoin transactions. And say we have we have these Peggies here who all want to prove that their Bitcoin transaction is valid. So they all want to prove that their commitments are in a certain range. So, but they don't want to reveal the secrets to each other, right? They don't want to tell the other Peggy how much they're sending. So how can they do that? Well, the trivial solution is they can just concatenate their proofs. But there's actually a better solution here with bulletproofs. We designed a so-called multi-party computation, an MPC, a custom NPC, not a generic one, which allows these Peggies to interact with each other and create a single proof for their joint statement. And this works if the statement is of the form that each party wants to prove something, and the overall statement is the conjunction of the individual party statements. So for example, for a range proof, if we have n range proofs for n provers, then they can use this MPC to create one single proof. And here again, the logarithmic scaling of the proof makes this a very worthwhile thing to do. So the protocol has a logarithmic number of rounds and a logarithmic number communication, but rounds are actually very expensive, or the communication is very expensive and complex, so there's also another variant of the protocol with only 3 rounds, but a lot more communication cost. So what is the overall evaluation of this scheme? Well, the overall evaluation of the scheme for confidential transactions, our main application, is that we have 670 byte range proofs instead of 4 kilobytes previously. And if we have 2 proofs, this is better, and the larger we go, this again, you know, for 16 range proofs, we're still under a kilobyte versus 61 kilobytes for the previous system. And the nice thing is, if we say want to double the precision, this only again adds 64 bytes. And overall, if we look at the current UTXO set and do not assume any change of user behavior in Bitcoin, this would shrink the size of the UTXO set by about a factor of 10 with respect to when, as opposed to if they had used the old range proof. And there's this simple protocol for users to combine their transactions, which is called a coin join protocol. So Monero, which is a privacy or a cryptocurrency that has some sort of stronger privacy features, is actually planning to implement Bulletproofs. And they say, bottom line, Bulletproofs are awesome, they work, the fees are lower, and they're moving into testnet. So we're very excited about that. I also want to, but Bulletproofs do not only work for range proofs, they're generally applicable, or general proof systems for arithmetic circuits. So let's compare them again to some other proof systems. So for example, again, snarks, the proof size are very short, they're constant. But again, the logarithmic scaling means that for sort of most proof sizes that would be considered reasonable, the proofs stay under 2 kilobytes. This is in contrast to another proof system called Starks, which also doesn't have a trusted setup, where the proofs are over 200 kilobytes, even though it also has logarithmic scaling or log squared scaling. So I also want to highlight, so Zero Cash, which is another cryptocurrency with the strongest privacy properties, which uses snarks right now. They're using a new circuit, so if we use Bulletproofs, the transactions would be about 1.3 kilobytes. However, the other big downside versus snarks, why can't they just switch to that? Or one thing is obviously, yeah, the transaction size would be bigger, but the other downside is that the verification time for Bulletproofs is linear in the size of the circuit asymptotically, versus for snarks, where the verification time is constant. So in practice, it would mean that the verification is about a factor of 10 slower. Let's talk about some other applications for Bulletproofs. So one applications are so-called proofs of solvency, or provisions, which was a paper in 2015 presented at CCS. And the idea is that Bitcoin exchanges or Bitcoin banks can prove that they're solvent without revealing why they're solvent. So they don't have to reveal what Bitcoin addresses they own. They don't have to reveal how much each customer has or how much money they even have in total, but they can prove that they're solvent. And with Bulletproofs, the size of this protocol would go down from 18 gigabytes to 62 megabytes. So quite a drastic change here. Another applications are so-called verifiable shuffles, where multiple parties have multiple messages, and they go through something called a mixnet. And as part of this mixnet protocol, every party needs to provide a proof that sort of n inputs are equal to n outputs, and that they were shuffled correctly. So that you have 2 lists of commitments, and you want to prove that sort of the same values were committed to in both of these commitments. And with Bulletproofs, this seems to be the first logarithmic-sized verifiable shuffle that doesn't have a trusted setup. We also implemented Bulletproofs into the Bitcoin cryptographic library. we spend a lot of our time on optimizing the verifier, and it turns out now that Chain Company or Chain Inc. has done a newer implementation in Rust, and they use AVX2 and Curve 25519, and that one seems to be even faster, so we're actually quite happy about the competition there. But one thing we did in the verification is we tried to make the verification as efficient as possible. So we took our fairly complex verifier protocol and boiled it down to basically just a single multi-exponentiation. So these x's here are elements from the are derived from the proof. And again, right, the proof is logarithmic size, but you can then expand the proof into a linear number of elements. So that's why the verification is linear. And then you just have to check the single equation, which is called a multi-exponentiation. So why does this help us? Well, say we want to check two proofs. So we have, which means we have to check these two different equations. Okay. But what we can do is we can use this this old trick to called a batch verification, to combine these two verifications by just taking a random linear combination of them into one big multi-exponentiation. And because the exponentiation part is a lot more expensive than the scalar operation, this will give us a big win. Because it means that verifying the first proof, say this is for two range proofs, is 6.2 milliseconds, but then each additional proof is more than a factor of 10 faster. Because again, right, we only have to do additional, almost only, the additional operations are almost only scalar operations. So what does this look like? So I plotted here the proof time, on a log-log scale, the verification time, and the batch verification time. And as a benchmark on our system, I also plotted how much does it take to verify n ECDSA signatures, which is what you would have to currently do in a Bitcoin transaction. So, and on the x-axis, we have the number of range proofs, the number of aggregate range proofs that we are verifying. And it turns out that starting from about 16 range proofs batched into one single proof, verifying 16 proofs is about as expensive as verifying 16 ECDSA signature. So if you have a system there, it isn't actually that much more expensive, or it's almost the same cost as the old Bitcoin system where people have to verify ECDSA signatures. I also have a small comparison to other proof systems, and you know, the space is getting larger, and there's a lot of exciting development happening here. And the core properties of Bulletproofs, where it improves, is that these are really short proofs with no trusted setup. And the downside, though, are that it has a linear verification time. So for really large circuits, it won't. The verification time will get prohibitively large, and it uses public key crypto, which means that it uses discrete log-based crypto, which means that it is not secure against quantum computers, unlike something like a Stark, which has other downsides like the larger proofs in practice. And the important thing to remember, there's something missing, is that the space is developing, and there's the trade-offs are very high dimensional, and there's really no clear winner here. And for example, on Wednesday, we will see 2 more talks on Hyrax and VRAM, which provide other trade-offs in this high dimensional space. And it really depends on your application which proof system is the best. And you can check out our paper on this URL. Thank you very much.
Is this working? Thanks for your talk. So I maybe missed this, but when you do the batching for verification, is this proofs coming from the same prover, or can you batch proofs from different provers?
No, very good question. No, you can batch proofs from different provers, and actually you can even batch proofs for different statements as long as they're roughly of the same length, or if they are of the same length. Because the generators are fixed in the common reference strings and are always the same for all parties, and the only thing that changes are the exponents. So that's why you can use the batch verification trick even for different provers or even for different statements.
So you don't need to change the prover protocol, in order to batch at the verification?
No, this is a purely verifier site.
Oh, and one more question. What is the asymptotic complexity for batching the proofs?
So the verification is still linear. However, now it's a linear number of scalar operations and only basically a logarithmic number of crypto operations. Versus if you just verify them normally, it's a linear number of crypto operations.
Okay, thank you.
Peter Neumann, SRI. Can you go back about 3 slides?
I cannot do that, but maybe.
To the slide where you have the 2 products equal to 1 mapped into the 1 product equal to 1.
The batch verification, yeah?
The left side implies the right side. The right side does not imply the left side.
That is a very good point. However, if the sort of the randomness is drawn from a large enough space, the probability that the right side will not imply the left side, it's inversely proportional to sort of the space where you're drawing your random scalar off. Maybe we can talk about this offline.
That's okay, thank you.
Okay, we can only make time for one more question.
Hello, so this is Attila Yavuz from Oregon State University. So it's also a great work. Just a question about, so are there any of proofs that operate in the lattice domain? Because there are lots of digital signature develops that are based on Fiat-Shamir transform on lattices. So do you see that these techniques are kind of extendable or applicable to lattices so that they could offer post-quantum security?
Yeah, that is a very interesting question. The question is, or the technical challenge is whether you can find a commitment system or a commitment scheme that has the same properties as these discrete log-based commitments in the lattice setting. But there's no sort of fundamental reason why this isn't possible.
Okay.
But yeah, it's an interesting question. Yeah.
Okay, thank you.
Okay, let's thank the speaker again.